Swayam Prabha. Digital India. Educated India.
Hello everybody. Today we shall be taking a very important topic in vacuum technology, that is a case study of system design, which is going to act like a tutorial for you for all the upcoming application systems. Well, the concepts that are going to be covered in this lecture are different aspects of pumping systems, chamber design, then thermal design like heat transfer, etc., and also the design for materials, degassing studies, and also little bit of some calculations for thickness calculations, and of course, the way you have to operate the system, certain precautions to be taken, all that will be covered under these concepts, and these are the concepts given in this slide. You can go through it at your leisure. So, coming to the introduction of vacuum furnaces. Well, why we have taken this? Because this is mostly working in the range of 10 power minus 5 to minus 6. That is the starting point of high vacuum, and they can be extended concepts to ultra high vacuum. And the initial evacuation problems, particularly for heavy vacuum furnaces, are very specialized. That way you will get a flavor of most of the issues in pumping and calculations of thickness, chamber, like that. So, that is why we have taken up this case study. What are vacuum furnaces? They are very useful in day to day life in various industrial applications, because they offer a very pure protective atmosphere while melting, casting, shaping, brazing, variety of metallurgical applications, which are very important, because without materials no process can be done. And while doing that, metals have got a tendency to pick up oxygen, nitrogen or hydrogen, things like that. So, if you do it under vacuum, these problems can be eliminated, and that way the property of the materials with which you will make various gadgets in day to day life, it will be very good, because the strength will be improved, some thermal property will be improved, corrosion resistances will be improved, because they are all related to microstructure. So, even vacuum heat treatment is as popular as vacuum melting and casting. So, there are a whole lot of furnaces of different volumes, very large volumes of this room size, and to a small but very high tech jobs for alloy fabrication, etc. So, these are all very day to day high tech applications, and they will form the starting point of all ultra high vacuum applications, whether it is a semiconductor or space or nuclear, and they will also take up some concepts from medium vacuum applications. So, in this design of that, what we need to do is pumping systems have to be designed. So, that we have seen already in lecture number 20, where we have clearly explained you the selection criteria. You go through that again, but furnaces mostly diffusion pumps and rotary and Roots blowers are employed for boosting action. You can have high tech pumps like cryo and turbo pumps, but most of the applications in large industrial metallurgical furnaces, even today people use cost effective diffusion pump based systems, and varieties of components you have to finalize in vacuum systems, particularly when it is related to furnace applications having huge throughput, and it has to be compensated by a variety of pumps with boosters, a very large capacity consuming a lot of electrical power and water circulation requirements, and volumes are big, masses of the pumps are big, chambers are big, interconnecting pipings are big, and most of the time you use very specialized valves like gate valves because they have high conductance. Sometimes you may have to use a hogging pump initially to evacuate fast from the atmosphere to 10 power minus 3 torr. Afterwards, during the initial vacuum to 10 power minus 6 torr, you may not require a very good backing because the load is not much, because process is not on. That means melting or casting or heat treatment process is not on. That means electrical heating has not been started. So, during that time a small pump may be good enough, booster can be bypassed. So, all these techniques, it is a form of vacuum system design, not just pumps. How do we minimize the electrical power requirement, maximize the conductance of the pipings and optimize the pumping speeds at various intervals of time, but without compromising on the quality of the final metallurgical microstructure, which is going to play an important role to make all these materials and even component level, so that they will form subsystems for various other industrial applications. So, you have to keep track of various design aspects, conductances on one side, thickness calculations on other side, optimization of pumping speeds, electrical requirements and water requirements, it is all a part of the design. You have to explain to the operator as well as the repairer, because troubleshooting also is a part of the design. Certain aspects of troubleshooting may not be required when you are using one torr application. Even with sound you can see there is a leak, and ultra high vacuum it is a different game altogether. Leak detectors RGS are built in, but here they will be trolley mounted sitting next to you. So, you have to bring it immediately through a coupling wall, you have to attach it without losing vacuum because it is a huge chamber. So, all these precautions have to look after, flexibility of coupling lines. There is a big piping network. That piping network will have an effective conductance, as we have already seen in conductance calculations and walls and various components calculations in lectures of 27 and 31. So, you can go through those lectures again. What is the aim of all this exercise? It is a part of design, but materialistic as well as thermal as well as mechanical and also degassing procedures, component level. Finally, you will find out conductances for the flow to take place, so that fast pump down takes place, as well as during the process huge pumping speed is available to take care of sudden huge increase in throughput when melting and casting is going on, and background vacuum should be very good, and during background evacuation the throughput is not much. That time it is only the ultimate vacuum that we have to check. So, that leak testing and troubleshooting should be done in the initial testing when process is not on. This is a very important aspect which others may not know. So, designer has to tell when to do the leak testing, etc. Do not do leak testing when things are already started, then costly materials will be lost. So, on one side you have a queue which is very little smaller compared to the queue when the process is on, because in addition to leak or outgassing loads, you are already having a process load now which is going to dominate. So, pumps have to be suitably designed. If necessary, additional pumps have to be brought in through necessary gate valves. All that you have to do by taking into calculations these most elementary calculations, most important calculations, that 1 by S effective is 1 by S maximum plus 1 by C. You know the conductances, you know the manufacturer's pumping speeds, find out the effective pumping speeds and use that effective pumping speed to find out the throughput or acceptable pressure if you know the throughput. Otherwise, you do something, either you take care of the conductances or pumping speeds, or for some time during the process on, if it is only a part of the cycle, you can suddenly open a gate valve having another pumping system, but as soon as it is stopped, when you want to take out and next loading is done, during that time small pumps. So, it is a whole lot of sequence of pumping connections have to be done. For everywhere you have to again calculate conductances, optimize the electrical power requirements, etc. So, metallurgical processes you get all these concepts very clear. Next, how do you design hot and cold walls where is this heat coming, how do you optimize this heat so that it is focused for the job. That job may be melting, casting or brazing or joining or heat treatment. You should not waste this heat somewhere. Of course, there are varieties of techniques and it is continuously getting improved. There is a lot of mechanical and heat transfer design. There are two types of furnaces basically, hot wall type of furnace and cold wall type of furnace. Cold wall is more popular. Let us see why. In hot wall furnaces, there is a big vacuum chamber. I am not showing inside jobs etc. With respect to wall I am talking, and these are the heaters, these dots are heaters distributed uniformly, and the entire chamber gets hot. That as a hot chamber it will radiate to the job, that way you get heating, and that is how it looks like a vacuum furnace. But you see here the chamber is acting in two ways. One, it is a vacuum chamber, the other is it itself is looking like a heating element with respect to job, because there may be background heater, but they are all located in atmospheric pressure. So, first interface is vacuum chamber, from vacuum to the atmosphere, and heaters are outside. So, for the hot zone the chamber may look like a heater, and all the seals for hot zone type of things, hot wall type of things have to be compatible, because chamber itself is very hot. But you will get one advantage, degassing will be very good. So, there are some advantages and very specialized applications, if you can use metal seals or if you can cool that area of seal etc., very large scale chambers. And the entire furnace is in laboratory. So, if heater is outside, the room will get very hot. So, you have to have insulations, thermal insulation, all these aspects will be there. It may degas, it may give some smell. So, you have to take care of all that. So, there are some advantages, there are some disadvantages, and finally, how much electrical power is required and all, you have to calculate to the heat gained by the job and heat lost to the other thing. That means, the exergy of the energy that you have given, how much it is really transferred for furnace purpose. Whereas, in cold wall, the wall which is a vacuum chamber, again cylindrical vacuum chamber, it is surrounded by another chamber, but that is not a vacuum chamber. The annular gap is used for flooding it with water, so that if the chamber gets hot, the water will take care. So, it is basically it is not like a double walled chamber of a cryogenic vessel or a thermos flask. The second wall is basically an atmospheric wall, even inside also. Instead of air, you have got water circulation. So, that way it is called a cold wall. So, all the gaskets etc., they will not be in trouble, they will not degas, they will not suddenly melt and all. But disadvantage is the chamber is not properly degassed. So, you have to take initially to purge it properly, run the air blast for a longer time, all those issues a part of the design or scheduling has to be done accordingly. Inside now, this insulation is now inside, because inside there is a heaters, there is some radiation shields, so that heat is not lost to the outside. There should not be radiation shields inside. If you put shield, job will not get hot. So, how do you locate heating elements, how do you locate radiation shields, and surrounding all that, this hot zone, how do you locate the insulation properly, which should not degas under vacuum. So, those problems you have to solve it. The type of problems, design issues for cold wall are different from hot wall, and resistive heatings, induction heatings, varieties of things are there that we will see later. So, in this design, hot or cold wall, most of the time in industrial applications cold walls are good. So, once you decide cold wall furnace, then how do you calculate the design criteria? Now, let us zoom a cold wall furnace. I am showing the double wall here, and there is a heating elements here, there are radiation shields, there is a support structure to support all of them, it cannot stay in mid air. So, there will be heat transfer through the support structures, which you have to calculate a part of thermal design. There will be radiation heat transfer from here to that side, that is minimized by multiple shields. They are also high temperature grade materials, there can be stainless steel or molybdenum, we will see later. And this entire chamber is supported inside that vacuum chamber, and there is a water circulation jacket, which I have already explained, supported by the legs. This is schematic, but it is a very big chamber, sometimes 2 meter by 5 meter type of thing. This is connected by a valve which can either go to the backing mode is this side, or roughing mode, because the rotary pump initially has to evacuate the chamber, later same rotary pump will be serving the purpose of backing a diffusion pump, and there will be shields, Chevron baffles, etc. So, design should include effective pumping speed calculations and how much should be the pumping speed, matching of this pumping speed with this backing pump. Sometimes hogging time you may have to use a bigger pump, later you may get a small pump which is a hold pump, and if it is required you may have to add here a roots blower, and when to add, when to bypass, and put a small purging valve, so that initial purging is taking place, and what type of materials you have to choose, that is also part of the design. Most of the time shields and controls and valves, after deciding you have to see the main chamber, whether it is 304 or 316 depending on the vacuum level, and then thickness has to be calculated. How do you go about thickness calculations? First you have to know the pressure, like any vacuum vessel we have seen in lecture number 26 and 28, we have seen materials and thickness calculations. We have very clearly explained you how various types of metals and alloys which are used for chamber materials, and depending on the yield strength, depending on the temperature, the thickness has to be optimized, taking 1.3 atmospheres is the pressure difference in absolute scale, because inside is the vacuum. And here of course, little bit of excess value you have to take because of hydrostatic pressure here, that is there because of water. And if you take that and then go ahead with calculations we have done in lecture 28, exactly similar tape. Since it is a tutorial, we will again do for you. So, for a vacuum application, we have seen fabrication issues after the design are over, whether it is a welding, brazing, etc. But normally argon arc weldings are very popularly used, but it all depends on the budget finally. So, you have to be careful in choosing materials and joining procedures. So, once you understood the system properly, then once you make this 0.13 megapascal, which you have seen in the 28 lecture, and that time we have taken 50 centimeter type, because vacuum furnaces are typically 1 meter dia and 2 meter long type of things, where you can have front side a quick open door, or there can be bottom or top openings depending on the type, we will see later, and weldings will be there here, and dout gassing has to be done, leak testing has to be done. But right in this slide I am going to discuss the thickness of this. It is already discussed in section 28, you go through it, because there it was details were given. Here I am just giving a recap of the same thing. Let us choose a guess thickness 5, then ID will be 10 to 1010 millimeters, then you will have an L by D ratio, and you have an ACME charts for different section 8 for different D naught by T curves. On that D naught by T calculation, in our case this is 1010 by 5 mm guessed thickness, you will get 202, and this is L by D ratio. So, this 1.98 you go here for that 202 line and get one factor, a dimensionless factor called A. Once you get that factor, go now that was geometry is over. Now, go to the material properties and temperature of operation, etc. More important, because these are furnaces. Temperatures are not always room temperatures. Go to those temperatures. In cold wall, it is mostly room temperatures. So, you can use the same formula which we have used in 28, 4 B by 3 D naught by T. This B factor is obtained from this second curve after getting the A factor from the geometry considerations. We have seen in lecture 28, you follow the same steps. For example, here I have done a design for this vacuum metallurgical furnace. I have chosen initially different thickness, and it is coming out to be not suitable. Okay. So, what is the thickness? 4 millimeter. Then immediately L by D naught by D, A and B factors, whether the safety this is PA is more than PD or not, that condition if you check, PA is coming about 0.074, whereas design pressure is 0.13. So, it is not suitable. Then increase it to 5 mm, then immediately things have changed for the same L and D, then you get 0.15 which is more than 0.13. So, this is how we finalize, then give your safety, but after that you have to do finishing properly inside. So, strength, then leak detection, that is also again parallelly other issues of design. So, once you do that, you are decided cold wall, you have made the design calculations, then you will have to see whether it is a very heavy furnace where you will be loading the main load which is to be heat treated or something from bottom, because you cannot just load things like that. It is not a small sample in a semiconductor industry where a silicon wafer will be loaded. It is not like that in a metallurgical process. Big ingots, big some 1000 kg maybe. You have to load it from bottom loaded for heavy jobs. From top load, if there is a hoist and the weights are reasonable, you can load it from the top. Front side for quick loading, and if it is long pieces lightweight, then you have to use front loaded. So, all these chambers and what are type of O rings you have to use, and the fabrication from the sheet, how do you roll it and weld it, depending on the furnace you have to select. Once you are selected, the stresses to be also solved. For example, instead of cylindrical design, if you take a rectangular design, maybe you will get more volume for working volume, but there will be stress concentrations on welded zones, and problem for leak may be more. But if there are certain specialized situations, cylindrical design is not allowed, and hot chamber, hot wall type of designs, even cubical things are used for very specialized applications, if you can take care of that. Similarly, water cooling etc., if you go to 1400 degrees centigrade etc., you have to take care of water cooling circuits, then budget has to be worked out. At 10 power minus 5 torr, you have to be very careful. This I have told you yesterday also, earlier also. If you by chance leave some water drops, or if there is a leakage of water from that outer shell inside, that will become millions of liters at 10 power minus 5 torr. That should be taken care properly, and this can be checked by a residual gas analyzer with the H2O peaks etc., and leak detection has to be done now and then. Okay. So, after deciding whether it is front load or bottom load or top load, after designing fabrication issues and leak detection design, then we have to design the hot zone properly. What do you mean by hot zone properly? You have to design the type of elements, heating elements, type of shield materials, because you have to heat, you should see to that heat is not lost to the surroundings, and it should be confined properly, degassing should be minimum, and volume should be optimally used, and the pumping speed should match. So, you have to take care of all that. For example, Canthal can be used up to 900 degrees, but sometimes after a long time, because of chromium losses, they may not be properly working. Then molybdenum is ideal for most of the furnaces, molybdenum is used up to 1400 degrees. But if you make strip type of things and sharp edges, when you make high power, when to go to high temperatures, the electric fields will be high, you may get discharges. That is going to be dangerous in a discharge in a vacuum chamber. So, you have to take care by keeping a thick round type of things. Then making a heating element from mechanical structural point of view may be difficult. So, there are if and but, you have to choose accordingly depending on the temperatures. At times you may have to take hard decisions that I will not go up to 1100, maybe 1000 only, like that. And also heating has to be done slowly, steadily. So, you have to have a programmable controller etc. Uniformity of the temperature is very important. Thermal uniformity zone is extremely important. That is how you have to decide radiation shields etc., etc. And if you want to go for very high temperatures, tungsten is the only way, tungsten or tantalum can be used. And you can put these heating elements, 2 elements, 4 elements, 6 elements, octagon, hexagon, so that you will work out from your heat transfer radiation principle, solid angle suspended, optimize it in such a way the job gets more heat and shieldings will take care, loss will be less. All this if you can take care. Graphite is the ultimate which can stand 2200, but graphite should not be used always, it can contaminate your this one, because carbon contamination is not allowed in certain alloys. You have to take care of all that. And the diffusion of the carbon is also very important. If you can take care of that, accordingly you choose the heating elements. Once you choose the heating elements, then water cooling etc., pumping etc., then you will have to choose whether you will use shields, multiple shields. So, this paragraph is related to this figure. You can use multiple shields to take care that heating zone is adiabatic, so that heat is not lost to the surrounding. How do you arrange these heating shields is a design problem, beautiful design problem, okay, solid angles etc., which For lack of time I cannot see, but later if there is a time in some other application we will cover it back. And highly polished surfaces have to be there, because emissivity should be as small as possible, so that heating is totally given to that job. So, all that you have to know the heat transfer designs, not only the shielding, but also thermal insulation outside and suspended radiation to heat transfer calculations have to be done. Now and then they use induction heating also, where it is more uniform and stirring is also coming, as there are some advantages of induction heating, where homogenization takes place, and brazing and casting and sintering and all. Sintering they will use electrically heated, but casting, melting and all, vacuum induction furnaces are getting more and more popular for aluminum alloys, and the entire this cup containing that molten material with alloy additions etc., it will be tilted. So, there is a vacuum rotatable joint here, so you have to be very careful. This type of components are available commercially, you can use that, otherwise you will have to develop a rotary seal here and then cast it on bottom in a big tray and insulate all those things, structural supports. So, these are all various issues you have to take care of: insulation, shields and support structures. And associated with all that, uniform heating. Initially when you switch on the heater, the heating rate may be very high, sometimes it gives trouble, because huge temperature differences from the heating element to the job. So, radiation can be very high, but you should reduce the electrical power at that time, so that uniform heating zone. There are very good programmable power supplies are available. Then there are equally good amount of troubleshooting techniques connected to the furnace, like degassing, RGA and leak detectors etc. They are very essential, and this microprocessor should look into that, whether I should go for leak detection scheduling or pumping scheduling, or open some other valve to make suddenly hogging action up by another pump, and electrical powers have to be adjusted, water should be switched on or switched off, or if there is a emergency situation where there is a huge water peak is coming, something wrong, somewhere some joint is broken or leaking, or some gasket is very hot, immediately switch off the process, otherwise costly materials will be lost. You have to take all that and use the proper thermocouples depending on the range, and thermocouples should not degas, and thermocouples the end should be spot welded. You cannot braze solder, because at that temperature solder will come out, and you cannot, if you twist it, twist length should be minimum. If it is a long twist and you are touching that, and it is actually measuring, first junction is formed in the bottom of the twist and it may be 30-40 degrees. And in vacuum some other important thing takes place, that is here I am telling you. Whenever it is sandwiched or heating or shielding or even thermocouple is stuck, if it is not properly stuck with enough force with nut and bolt properly, there may be vacuum gap now. Atmosphere pressure we do not see, I can touch, I will get same feeling if I touch some heater, but in vacuum if I touch and if there is a fine vacuum gap, there can be 100 degrees error in the measurement. This may be 400 and thermocouple is here, because of some thermal expansion or some loosening or something, it got little loosened. It will measure 400 will be shown as 300. That is the problem. Substrate heaters in semiconductor industry, sometimes we think substrate heater, if you keep thermocouple it is showing 400 degrees, but actually it is the silicon may be at less temperature. You have to keep track of that. So, you have to tighten here and there, so that through those conduction rods front end is also heated. These things we will see in semiconductor when thin film manufacturing again. Okay. So, sensitivity of the thermocouple has to be chosen. Once you do all that, still lot more issues are there, heat transfer issues, heating elements, after all these furnaces. Same thing in substrate heaters in semiconductor manufacturing. But these things are not much in particle accelerators of ultra high vacuum. There will be some heating for degassing only, otherwise it is a cool process. High voltages will be there, high magnetic fields will be there. That application is a different game. That time system design should do what? How do you separate cryogenic environment from the vacuum, etc. We will see there. But here the two famous formulas which are known to most of you, Stefan-Boltzmann equation, taking emissivities and shape factors into consideration, and that because in vacuum the only process of heat transfer is radiation, convection is not there. At 10 power minus 6 star radiation, residual gas conduction is not there, but there will be one solid conduction because of support rods. For example, you will see these are all heaters, these are all shields, this is the furnace and this is my gasket, and there is a front end shield also, this is a quick opening door and electrical feed throughs for electrical things and gas inlets, varieties of things are there, and the gasket should not be heated. There can be double gasketed, sometimes very big furnaces they will use double gaskets, and in between that space between two gaskets is evacuated by a small pump. It will immediately reduce the leak rate from here. That is one thing I have not shown, but it is being done in most of the very large scale furnaces. Okay. And you have to know the emissivities and use the radiation formula for heat transfer to the job finally. Job will be here finally, and heat loss to the surroundings from the radiation to the chamber, and conduction through the chamber through the unavoidable support structures. If you can do all that, the heat flux is properly utilized to reach the temperature. So, these heat transfer calculations I leave it to you. You can easily understand the various temperatures, and you have to do iteratively. What will be the shield, how many, if you have 4 shields, 5 shields, what will be the loss, how much is the heating for an I square R, and that heat if you take, how much is being radiated, and otherwise how much is the equilibrium temperature of the heater. All that you have to calculate using these heat transfer equations. Once you do that, you are ready now. Then you can take care of the furnace. The furnaces will look like this. You can see here there is a big rail type of structure. Whatever you have to send, you can send it inside. There are heating elements and shields, front door and pneumatic couplings and variety of electrical pipelines and water pipelines and pumping systems and big elbows and diffusion pump here, then backing rotary pump and roots blower will be the other side, heating elements, electrical transformers for power supplies, and entire thing is a microprocessor controlled, and he will see the mimic diagrams which valve is opened, whether this is a hydraulic, see this is a pneumatically operated valve, immediately the valve will open very slowly. Before that you have to take care by the penning gauge to get -5 torr. At that time sudden fluctuation should not take place. If necessary, roots blower has to be switched on, otherwise you can bypass it. And during closing, and again when you close the door, and finally you heating up, that time heavy load will come. So, you have to be careful when to use hogging pumps, etc. Again everything is done, cooling is also should be done very carefully. At that time you have to open the door, during that time venting should be done very carefully. If there is little positive pressure, huge amount of force will be there to quickly open and it will hit your face. So, that time very sensitive delta P indicators, preferably you can use even water U tube, highly sensitive. With a valve, do not put water U tube or continuously corrected, only during the venting time, during the purging time you connect this. That is the design again, what should be the throughput, etc. Slowly design, vent it, but you can check finally after all that purging is done. For few seconds you just check, anyway it is atmospheric pressure, now it is not going to degas, this water will not go inside. At that time you check delta P's, it is almost 0 settling, at that time open. There were accidents in furnaces in the last operation, everything was success, at the end it is a problem. It is like operation success, patient death type. So, that will be a problem, and sufficient temperature should be, proper temperature should be there when you are opening the door. That means sufficient cool down should take place, that heating, soaking, melting, casting or heat treating, again cooling down, it is a programmable thing, you have to take care of that. Similarly, conductance calculation, pumping speed calculations, it is a beautiful thing, you have to use all our earlier knowledge. This is only a tutorial that we are giving in heat transfer calculations and pumping speed. Finally, you are designing, you should keep in mind optimize the thickness, so that materials, costly materials need not be purchased unnecessarily, and connecting rods in the support structures, you have to choose properly, otherwise huge mass will be there or huge heat transfer will be there. Exergy calculations you have to do, and maximizing the conductances by gate walls and minimizing the budget is another important thing, and interlocking safety is the most important thing. Unless rotary pump is on, diffusion pump should not be there. Unless you get a good vacuum, heater should not be done. Unless the H2O peak goes down, process should not be there. Unless water is on, process should not take place. Unless the front door is properly closed with good setting, nothing should switch on. So, varieties of things you have to take care. If there is a spark inside because of that 40 volts reaching of molybdenum heating element, you should immediately take care of that. Okay. So, pumping systems, valves, control panels, it is a huge lot of design issues are involved, interrelated. We have seen with an example, and in future we will see how these concepts with earlier detailed concepts knowledge of various pump down and system calculations, how we are going to use them in the application in the coming lectures. Next 20 lectures will be on process applications. So, you will see a big vertical, high nice looking furnaces are available nowadays. So, finally beauty matters. You should make it and also beautiful, comfortable. Such things are valid for every vacuum system, and that is a part of the designer. Designer should also finally make it an elegant system. Okay. Thank you very much.